So I'm going to talk about a paper with Daniel Bauman and Dan Green that we wrote a few months ago. And I'm going to tell you about results with two different applications. One is to RG flows, and the other is to the effective field theory of inflation. So to set the stage here, here's a picture of anti-de Sitter. So in ADS, we calculate boundary correlation functions at the edge of this diagram. In de Sitter, or in inflation, we're interested in correlation functions at scri plus, at future infinity. And these are relevant for inflation and the CMB. So as is well known, in ADS, so the RG scale corresponds to depth into the bulk. And the analogous statement in de Sitter is that inflation is not exactly de Sitter, it's quasi-de Sitter, where the de Sitter length is changing slowly as a function of time. And that change of the de Sitter length with time is the slow roll of inflation. And so that direction is analogous to the RG direction in ADS. So that's what connects these two topics of RG flows and cosmology. And what we're going to do is we're going to study correlation functions in these two different setups, and then use dispersive techniques on CFT correlators to try to write down some new sum rules and constraints on the theories that you get in these two different situations. So that's the plan. So, of course, these two geometries are very similar, but also very different. They have similar symmetries. You can formally Wick rotate between them. The Wick rotation acts on the space and time coordinates, and also sends the cosmological constant to minus itself. So formally, you can do this. And there's a long-standing question of whether you can really make sense of this as a DS-CFT correspondence. The Wick rotation, of course, really makes a big difference when you start trying to talk about quantum mechanics. And it's not clear whether there really is a DS-CFT for quantum gravity. But I actually won't be using it. I'm just going to use the kinematic relationship that you get from this Wick rotation. So there's a question of whether there's really a holographic theory of de Sitter. And I'm not going to wade into that in this talk. I'm just going to use the kinematic resemblance. There's certainly a formal correspondence between certain observables that you can calculate at scri plus and de Sitter, and correlation functions that you can calculate in CFT. So in this talk, I'm going to describe some observables where we can use this rotation to derive some new results for cosmology. The final results about the effective field theory inflation could have been derived directly in de Sitter. So these are just facts about quantum field theory in de Sitter space, and slow rolling de Sitter. And don't rely on any speculations about DS-CFT. But you'll see why I want to go through the holographic problem as an intermediate step. And also, just the problem of understanding RG flows in ADS is an interesting problem on its own. So we're going to be able to sort of treat these two things step by step together. OK, so first I want to set up the theory that we're talking about in inflation, and then we'll do the same thing in ADS and start deriving these new constraints. So in inflation, the de Sitter radius is increasing in time. So Hubble is decreasing. And there's an effective field theory that captures the dynamics of this, that captures the symmetry breaking pattern when you have the broken de Sitter symmetry that's broken by the time dependence of the Hubble factor. So the way this effective field theory of inflation works is to expand around some background, the inflaton and the metric, the rolling background breaks the time diffeomorphism symmetries, and you can use this symmetry breaking pattern and the Stuckelberg trick to find an action for the Goldstone boson pi. And the effective field theory of inflation is that Goldstone, is the action for that Goldstone. It's for the action for the Goldstone for the breaking of time translations in a slowly rolling de Sitter. So we're going to be talking about constraints on this theory, so I want to dwell for a few minutes on what the kinds of interactions are that you see in the effective field theory of inflation. So we're going to stare at the Lagrangian for a minute. So this is going to be the first few terms in the effective field theory of inflation in 4 dimensions. Maybe I need my pointer at this point. Here we are. Okay, so it's a non-relativistic theory for the Goldstone pi. It's non-relativistic because the rolling background is breaking the symmetries. So the kinetic term looks kind of like a de Sitter kinetic term, but with this speed of sound parameter that controls the speed of inflationary propagations. So this is a parameter in the theory that we have to measure and experiment. Right, so as I said, this is called the inflationary speed of sound. And then there are nonlinear terms. So the interaction terms, there are cubic terms. Everything's derivative coupled, but there are cubic derivative couplings like these two. And then there are quartic derivative couplings like these, and then so on. There are higher couplings with higher derivatives and higher numbers of Goldstones. Because of the nonlinear symmetries that we're realizing here, the couplings of these derivative terms are not independent of each other. So these are related to each other by the nonlinear symmetries. So in particular, this speed of sound parameter shows up all over the place in the Lagrangian in order to match the symmetry. So it's showing up in the kinetic term, but then it's also showing up in the cubic interactions. It's showing up again in the quartic interactions, and it shows up in the others as well. So in the language of inflation, these kinetic terms are the standard slow roll theory, just the free theory, and the interaction terms are responsible for non-Gaussianities in the CMB. I'm going to be working the decoupling limit, which is a limit g Newton to 0, where gravity decouples from this. So the effective field theory of inflation and the decoupling limit is just it's a particular non-relativistic QFT for a scalar field, and that scalar field is now living in some fixed background. Now, we'd like to understand what the possibilities are for this effective field theory of inflation. It's just some particular type of QFT. We'd like to understand what kinds of theories it could be, and we'd like to do everything that we do for ordinary relativistic QFT, but for this QFT that's relevant during inflation. And the problem with that is that it's non-relativistic. Some of the things that we understand very well about relativistic QFT, like dispersion relations and constraints on the amplitudes and sign constraints on the coefficients, a lot of this technology has not been developed, is harder to develop and has not been developed in the non-relativistic case. And so there are basic questions that we know how to answer in relativistic QFT that we can't answer here, like what are the rules, what kinds of couplings, what kind of coupling constants are allowed, how big can they be, what sign can they have, are there constraints among them, some rules, dispersion relations. So this is generally harder than, answering these questions is harder in this context than it is in ordinary QFT. So there was a paper making some progress on this a few years ago by Bauman, Lee, Green, and Porto. And they made a couple of, so they derived some dispersion constraints, and they made some conjectures about quantum field theory during inflation. And it's these conjectures that I'm mostly going to focus on in this talk. So let me say what these are. So first of all, they conjectured that there should be some kind of dispersion relation for the inflationary speed of sound. This is motivated by the fact that it's obvious, it has an obvious sign constraint. Okay, so this quantity, the speed of sound, should be less than 1. And so clearly this combination should be positive. And often when you have positive quantities in a QFT, it's because you have some dispersion relation that relates them to something positive, like the discontinuity across a cut. They didn't find a dispersion relation for the speed of sound. So that's going to be the main goal here, is to find a dispersion relation for the speed of sound. And we're basically going to do that. There's a second part of this, which is that they wanted to understand what it means if we measure that speed of sound and find it to be very close to 1. So if you have a dispersion relation and it's saturated, then often what that means is that the corresponding cross-section, so the dispersion relation relates this coupling to a cross-section. So if it's saturated, it means the cross-section vanishes. And for the cross-section to vanish, the theory is just totally constrained to be free. Okay, so what happens in relativistic situations like this is that if you can derive a dispersion relation like this, and then you go out and measure and find that it's saturated, then just by measuring this one coupling constant, you can constrain the whole theory, all the coupling constants of the theory. So it gives you much more power from the measurements that you might do. So if this conjecture is true, then future observations can be used to constrain this entire effective field theory during inflation. So this is, as I said, contributes to the non-Gaussianities. So measurements like from Planck do constrain this parameter. The constraints right now are pretty weak. As you can see, we expect it to be somewhere between 0 and 1, and it's bigger than 0.02. But you could hope that that constraint will just, well, either we'll see the non-Gaussianities, or that constraint will just keep getting stronger and stronger. And if that's what happens, we'd like to understand what that's telling us about the full effective field theory of inflation. If we see that that's going to 1, we'd like to understand if that means the theory is free.
So there cannot be relativistic interaction?
Well, the relativistic interaction, what do you mean? When I say this scalar is free, what I mean is that the theory of the Goldstone boson in the decoupling limit, it has only the Gaussian terms. It's not that the full theory in the UV has to be free. Well, right, yeah, yeah, right. Is there a question?
So the number 1 over c squared is 1600, right?
Yes. It's not a very strong constraint right now. Yeah. Which is good. Maybe that means we'll see it. Okay. So this was sort of their wish list for these dispersion relations, and what I want to describe in this talk are attempts to make this work. So as far as the dispersion relation, we're going to derive a dispersion relation for the speed of sound. Okay, so that we're going to do. This question of proving that the theory that saturation implies the theory is free, this is a much thornier problem, and we're not going to be able to prove that. Basically, as we'll see, this is because we don't really understand the properties of the UV properties of amplitudes in de Sitter. And without understanding those UV properties, we don't get the second point. But we will get the dispersion relation. So the strategy is the following. First, we're going to set up an analogous problem in anti-de Sitter. As I said, we're going to consider this like an RG flow. And we're going to use recent CFT bootstrappy sort of methods to analyze this problem in anti-de Sitter. So there's been a lot of work, as I'll describe, on understanding dispersion relations in CFT. And what we need to do to address this problem for an RG flow is to take those methods for CFT correlators and apply them when the theory is not conformal, so when it has a mass scale. So that's actually, I'm phrasing this talk in terms of inflation because that's how I was motivated. But really, the bulk of what I'm going to be, our main results are really in point 2. So really, the results I'm describing are going to be completely clean and clear in the case of these RG flows. And then we'll do our best to go back to de Sitter, but as I said, there it's trickier to understand the UV. Okay, so really the problem that we're going to solve is the one on anti-de Sitter, and then we'll see what we can get in de Sitter. Okay, so we'll start with setting up this analogous problem in ADS, which I think is an interesting problem on its own. So the anti-de Sitter analog of inflation is a holographic RG flow. And we'll see that slow roll inflation is a slow limit of an RG flow. So a holographic RG flow is just a anti-de Sitter-like geometry where the scale factor is changing as a function of the radial coordinate. So there's this scale factor here that's z-dependent. This geometry is dual to a quantum field theory that's flowing from a UV to an IR fixed point. So we have the CFT in the UV, and then it could either be gapped or there could be another CFT in the infrared. In the effective field theory of inflation, this coupling, the coupling that was controlling so much of the theory that we were really interested in was the speed of sound. So in ADS, the analogous thing here is the speed of radial infall, or the radial speed. So if you compare dz and dt here, there's now a speed, a non-trivial speed function, which controls essentially how fast things fall into the bulk. So what we're going to study is constraints on this infall speed. I want to sort of explain what this means as an experiment. So if you imagine dropping an object from the boundary into the radial direction, so say you insert an operator at the origin, that creates an excitation that falls into ADS. In a CFT, it just falls in at 45 degrees. It falls in on the obvious light cone. So in the CFT vacuum, this infall speed is just 1. And if we translate this to a fact about conformal field theory, the dual fact about conformal field theory is that if you insert an operator at a point, then it'll just spread out at the speed of light. Okay, so we're talking about how fast an operator spreads out. If this particle is falling into the bulk, then the corresponding excitation in CFT is just spreading out along the light cones. In an RG flow, so in a CFT, this is basically trivial. It just spreads at the speed of light. But in an RG flow, there's some interesting dynamics of how operators spread as a function of scale. And holographically, that's captured in this infall speed. So now that speed will not be 1. The CFT, or rather QFT interpretation, yeah.
Is this speed 1 for the operator only in CFT2? Because I remember these discussions of butterfly speed, there was some non-trivial function of the dimension.
Yeah, this is no, it's always 1 in any number of dimensions. It's not.
Vacuum, that was important. Yeah.
Sorry?
Vacuum was important.
In the CFT vacuum, that's right. We're in CFT vacuum. So the butterfly calculation, well, I'll mention in a minute, but it's in an excited state. So it's in a thermal state, so that's a different story.
Here you're assuming that somehow the symmetries at the boundary, that there's no symmetry rating as you flow into them. At least when you wrote the metric as a function of z.
Am I?
For symmetry breaking in the x direction.
That's right. That's right.
And
Yeah.
you're assuming that this will be
Point. You mean breaking of the translation invariance?
spontaneous
Correct.
breaking of the
Yes, I'm going to assume that. Yes. Is that? Yeah, I'll just make an assumption. Yeah. OK, so in the QFT, the interpretation here is that we're deforming by a relevant operator. phi. So we start in CFT in the UV. And this infall experiment where we drop a particle into ADS is dual to a local operator that spreads out in time. So we insert an operator, and as I was describing, it just spreads out on the light cone. This is what happens in the CFT. But when we do this in a massive theory, then as it spreads out, it sort of changes which effective theory it lives in. So this is why I'm calling this a dynamical probe of the RG flow. It's spreading out in space as a function of time, real time, but it's also effectively exploring the RG flow, because at early times, this operator is governed by the UV fixed point. At late times, this operator is governed by the infrared fixed point. So the dynamics of function as a function of actual time t will correspond to will track the properties of the RG flow as a function of RG time. So as I said, in a CFT, local operators spread at the speed of light. But in general QFTs, they will not spread at the speed of light. There's a mass scale. And roughly speaking, what we expect to happen is that they'll start out, if you insert an operator in a massive QFT, it'll start out spreading at the speed of light. Then it'll notice, at some point, it'll notice that there's a mass, and it'll spread at some different speed. And if there's an infrared fixed point, it eventually will spread at the speed of light again. So this curve is a whole function worth of information about the RG flow that's telling you how fast things spread as a function of scale.
So the IRS gap just stays at this mass scale?
Yeah, that's right. Yeah. I think it would just stop, basically. Yeah. OK. OK, so this is the this spreading speed is the observable that we're going to try to study. Now, during inflation, the Hubble changes slowly, so it's quasi-de Sitter. And so the limit that we're going to look at in ADS is the limit where it changes, where this thing changes slowly. The scale factor changes slowly, so it's quasi-ADS. And what this means in terms of an RG flow is that the change of this radial scale factor is slow. Okay, so this is what you could call a slow RG flow, and in this limit, the infall speed is constant for a long time. Okay, so on the previous picture, we saw that there was this could be any curvy function here, just bounded by the speed of light. But in the slow RG limit, it's just a number. In the slow RG limit, you're looking at a limit where this spreading occurs at some fixed speed c sub z over a long period of time or a long range of RG scale.
Sorry, do these discussions assume that the bulk theory is local? If the bulk theory, the theory in ADS is very stringy, then...
No, that's right.
Don't have this kind of sharp cutoff.
That's right. So the pictures I'm drawing here are pictures that make sense in a holographic CFT where the bulk theory is a reasonable semi-classical theory. I think, yeah, and I'm only going to talk about that case when I talk about RG flows. I think there ought to be some analog of this in a general RG flow, but I don't know exactly how to define this curve, and I don't expect it to have sharp boundaries like it does in a holographic theory. OK. So I want to mention the butterfly curve that Raghu brought up. So there, it's a very similar idea. It's a similar picture. The picture that you could draw of the butterfly curve in holographic theory is the same picture, but it's a different experiment. So the butterfly curve measures the spread of local operators at finite temperature. So the butterfly curve is the same spreading of operators, but well, in the holographic case, you could consider a CFT, but at finite temperature. So it's the temperature that's giving you the scale. And here we're talking about the same effect, but we're discussing the spread of local operators. We're discussing the same spread of local operators, but now in the vacuum state of a non-conformal theory. So instead of turning on a temperature, we turned on a mass. Otherwise, it's pretty similar, but it's gonna probe something different for us. And if you want a precise definition of this, of these spreading curves that I've been drawing on here, then in holographic theories, the precise way to define it is to follow exactly the same procedure that you can use to define the butterfly velocity. So what you do is you take this particle in ADS, you drop it in, and then you use entanglement wedge reconstruction to ask where it lives, to bring that operator back to the boundary and ask how fast it's spreading. So the precise so I'm drawing all these pictures, but the precise definition of these pictures is from entanglement wedge reconstruction. We're asking how much of the boundary do you need in order to reconstruct this operator that's falling into the bulk. And you can define the butterfly curve the same way, by the same entanglement wedge method. Yes. I don't know. I don't know. I think in the slow, well, I think there's at least some limits where that can be done, but we don't really understand how to do it that way. Yeah. Oh, and I should mention in the slow limit that this whole entanglement wedge thing is sort of overkill. It really is just the same as the obvious speed you would get by looking at the metric and reading off dt dz. Okay, so in general, if you want the whole complicated curve, you have to go through entanglement wedge reconstruction. But in the slow limit, it's just very easy to read off from the metric. The other another quick aside is that there's another thing that I don't really understand, which is that this looks a bit like a theory that's scale but not conformally invariant, and that sounds strange because well, there's almost a theorem that there's no such thing as scale but not conformally invariant.
Why does this look scale but not conformal?
Because if I look at the RG flow at this time and calculate some correlations or functions or something, and then I compare that to what I would get over here, they're just related by a simple transformation. So as I move my boundary inward, nothing changes about the effective theory. Another way of saying it is that the coupling constants in the effective theory here are independent of, they're just numbers. They're independent of the scale. Like the fact that the infall speed was just a number instead of a function is like a scale invariance.
Isn't there a kink somewhere in the beginning?
Well, I'm not very good at drawing pictures. It's not supposed to be a kink. It's supposed to just sort of, it's supposed to start out at the speed of light and then go to the butterfly velocity. It's not a kink.
But then doesn't the transition period set time scale?
Yes, but
Doesn't that break scaling?
it does. But if this went on forever, then you would be if you take the limit, where the decoupling limit, then this just goes on forever, and you might worry about it. This seems a little strange. It does not actually violate any of these theorems. First of all, because we're at large n. But second of all, because the dual QFT, if you look at this situation, does not have a scale current. It's sort of a different type of scale but not conformal, where what happens is the theory has an operator which you can add, and adding that operator doesn't change any of the correlation functions. This is not quite the same as having a scale current, being scale but not conformal. But we don't really understand this. I just wanted to mention it. Yeah. Yeah, that's another way out. Yeah. So so we want to study this infall speed, and there's an effective field theory for RG flows, which was written down by Kaplan and Wang, which is very similar to the effective field theory of inflation. Okay, so now we're talking about anti-de Sitter, and the derivation is very similar, but now we're talking about ADS. The goldstone is the goldstone for the breaking of the radial scale symmetry. Okay, so this is essentially the dilaton of the boundary theory, and you can use the same Stuckelberg trick to derive the effective field theory in this case, and you can recognize all the same kinds of terms that we had before. So in the first line, this kinetic term, this was like the Gaussianity. This was like the Gaussian piece of inflation. So there's a non-trivial infall speed, but otherwise just a ordinary kinetic term. And then there's 3-point and 4-point and higher point couplings. But again, because of the nonlinear symmetries, the infall speed shows up all over the place in the interactions of this theory. So the goldstone in this situation is dual to the trace of the energy momentum tensor. Or if you like, there's an assumption here that the RG flow involves only one operator. This is like the fact that in inflation, this is the effective field theory of single field inflation. So there's an assumption that there's only one operator, and that operator is proportional to the trace of T mu nu. So what we have in the bulk is an effective field theory for the Goldstone boson. In boundary language, this is the generator of correlation functions of trace T. Okay, so that is the problem now that we want to study. We want to study this theory of RG flows in the slow RG limit. And now the plan is to adapt these CFT methods to theories that are flowing, and see what we can say about this theory. The advantage compared to inflation, so this is in the bulk. This theory breaks the ADS symmetries, but unlike in inflation, it doesn't prevent us from using the techniques that we know and love, because it's still just dual to a CFT in the UV. Okay, so we know the rules for this Lagrangian in ADS. There's no question. They are whatever the rules are for the dual CFT at infinity. So things like analyticity and unitarity and the UV behavior, these are all, at least in principle, completely dictated by the dual CFT. So I pointed out earlier that we don't really know the rules for Lagrangians in DS. In ADS, we don't have that problem. As I was saying, what we would like is a dispersion, some way of understanding this infall speed using these dispersive techniques. Okay, so we want a dispersion relation for the infall speed. The term that we're going to look at, well, we're going to have to include all the terms, but sort of the important term here is the fact that the infall speed controls the 4-point four-derivative interaction. And there are well-known constraints in relativistic theories. There are well-known constraints on terms like this, d phi to the fourth type terms that go back to work of Nima and others and earlier work. And so there is an interaction term like this in our non-relativistic Goldstone theory. So we might hope that we can derive some constraints on that term, and that's what we'll see. So we're going to use dispersion relations in the CFT. This is a story that's developed a lot over the last 4 or 5 years and has been applied to various problems. So I'm not going to go through all this, but I just want to point out the context here. So there's basically there's been developments in two methods of doing dispersion applying dispersive techniques to CFT. One is in position space, and the other is in momentum space. And I'm going to explain them briefly in a minute. But the two methods are pretty similar. They give almost the same set of constraints, but they don't seem to be exactly the same. And the two methods have been applied to various problems to derive constraints on ADS Lagrangians, the conformal collider bounds, energy and entropy conditions like the NEC and the QNEC, applications to conformal field theory, applications to understanding the Einstein gravity three-point function. And all of this is also related to the Karen-Huot inversion formula for CFT, which sort of ties together a lot of these dispersive constraints into one approach. So the basic idea of the dispersion relations is that when you have spin 2 contributions to the OPE, then you can extract these contributions from a dispersion relation for the CFT 4-point function. There are two ways to set this up. There's the position space method and the momentum space method. We've done both. I'm going to mostly use momentum space, but let me just mention both of them. So in the position space version, we look at CFT 4-point functions in a limit like this one, which is the Regge limit, where points approach infinity in a certain way. And what the dispersion relation gives you, lambda 2 here is a spin 2 contribution to the OPE. It could come from a spin 2 anomalous dimension or a spin 2 operator, depending on what theory you're talking about, but it's some spin 2 contribution. And the point of these dispersion relations is that you can extract that. You can write a dispersion relation that connects that to the double commutator, double discontinuity of the 4-point function. And this double discontinuity is positive by unitarity. This gives you a manifestly positive formula for the spin 2 contributions to some 4-point function. Okay, and unitarity in the UV is what gives you positivity in these dispersion relations. The momentum space version of this uses deep inelastic scattering. So in deep inelastic scattering, we define a state P, and then we imagine scattering off it with some probe. So the DIS amplitude is this 2-point function of the probe field in the state P. This is often discussed in the context of massive theories, where the state P is some massive particle. But more recently, it's been understood how to do this in CFT. And when you do this in CFT, this amplitude just becomes a 4-point function, because you can create the state with the operator O and then probe the state with the operator O. And so you just get O, 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 O. Okay, so these DIS techniques can be applied directly to CFT 4-point functions. The way that you apply this to learn about the spin 2 contribution involves defining some combination of momentum, the momentum transfer, which is usually called X, and then you do a contour deformation in the complex X plane in order to relate some spin 2 contribution to a cross section. Okay, so again, at the end of the day, you get some spin 2. So you get some spin 2 contribution, to a 4-point function related to something that's manifestly positive. In this case, it's the deep inelastic scattering cross section in the UV part of the theory. Okay, so the dispersion relations, it's important that these are connecting infrared quantities. So in this case, something that you can find in the OPE, like this spin 2 coupling, to UV quantities, like on the right-hand side, where this integral is over some high energy scattering, the cross section for some high energy scattering. Okay, so that's the, so we're gonna, so those are the, that's the background, those are the techniques that we're talking about here that have been developed and applied to various problems. And now we're gonna apply them to the problem at hand, which is this effective field theory of RG flows. So in the RG flow, conformal invariance is broken. Oops. Conformal invariance is broken, but actually these methods didn't really care about conformal invariance. These dispersion relations for the amplitude didn't really care about conformal invariance. So we can apply the same methods. We just are going to use the momentum space version, and we're going to apply these constraints to the trace of the stress tensor. So I'm going to work on momentum space and define a deep inelastic scattering for trace T. Okay, so we're looking at 4-point functions of trace T. And we want to apply this technology. So to calculate this correlation function, we're going to use the effective field theory of RG flows that Kaplan and Wang wrote down. In other words, we're going to just calculate this correlator in the bulk and then apply the dispersion relations. Okay, so this can be calculated by Witten diagrams. It's a little bit complicated because the Witten diagrams that we need are this is not, it's not an ordinary field theory in ADS like we're used to calculating Witten diagrams for. It has ADS breaking interaction terms. Okay, so you have to kind of start from scratch, but you can write down the Feynman rules and calculate the Witten diagrams. In this trace T 4-point function, so we're looking at 4-point interactions of the Goldstone. There are contact type terms, there are exchange type terms, there's a whole bunch of diagrams. It's a little bit painful, but you can calculate this amplitude explicitly. And then the sum rule that I was describing extracts the spin 2 contribution to these diagrams. So at the end of the day, that was getting a little technical, but now I'm just going to write the answer. So at the end of the day, what you get out of this is a dispersion relation for the couplings in a holographic RG flow. So here's what it looks like. On the left-hand side is 1 minus CZ squared. That's that term that we were expecting. It's the contribution of it's the radial infall speed. So we were trying to find a dispersion relation for this radial infall speed. The second term, so this one came from the contact diagram. The second term is a contribution from exchange diagrams, which depends on the details of the other couplings in the theory. So I think I have an equation for that thing somewhere, but it's not very important. It's just some polynomial in the couplings CZ and lambda, which are some of the couplings in this theory. So on the left-hand side, we have some couplings in the infrared theory. On the right-hand side, we have a cross-section for the trace T. So in bulk language, this relation, which is the main result of this ADS part, is a dispersion relation for the infall speed, 1 minus CZ squared, plus these extra exchange terms, which I wrote here in a little font so you don't have to read them. In QFT language, what this dispersion relation tells us is how fast an insertion of trace T spreads out. So if you insert trace T, then you can look at the operator spreading as a function of time or scale. And this dispersion relation is constraining how fast that operator is allowed to spread out based on this DIS amplitude. Yeah?
Maybe I missed it. What does the subscript UV mean on the integral?
This is just schematic for which regime of momenta we're integrating over. So when these dispersion relations are derived, there's a contour deformation. I'll actually have the contour in a minute, but so you calculate something in the infrared, then you deform the contour to the high momentum region, and so this integral is being done over the high momentum region. small x in the DIS variable. Other questions? Good. So I did this momentum space. We've done the contact term also in position space, and you get something similar. But the exchange terms were we didn't bother because we already had the result in momentum space. So now I want to make a few comments about this result, still in ADS, and then we'll go to DS at the end. First of all, if we take this infall speed to 1, then the left-hand side of the sum rule goes to 0. And so we have 0 equals the integral of something positive. And that's exactly the kind of thing that we wanted. We wanted a dispersion relation that would tell us that if it was saturated, then theory had to be free. So if you have a RG flow where trace T spreads at the speed of light, a holographic RG flow where trace T spreads at the speed of light, then the effective field theory, well, then at least this amplitude has to vanish. That's not quite a proof, but is evidence for the conclusion that if you have a holographic RG flow where signals spread at the speed of light, then the effective theory of trace T is free, is trivial.
Did the F squared term also vanish in this one?
What was F squared?
On your previous slide.
Ah, yes, it does. Yes. Yeah. OK, it's not quite a proof because there are higher, say, like a 12-point function or something won't contribute to this, and you'd have to do something fancier to get rid of it. But I think that could probably be done.
You're
Yeah.
also assuming that the other coupling, CR, vanishes in this limit?
Let's.
You have those other couplings.
Good. Let's see. Yes.
F was a function of
Yes. Yes. So if you take CZ to 1, then the only way for that term for the two terms to be consistent is if you send both of the couplings to 0, and the whole left-hand side has to become 0. OK, so this is a fact about holographic RG flows. I think that I'm phrasing this holographically because there we understand how to calculate the spread of operators. We can think about it as an infall. But I think it's an interesting problem to think about in general in RG flow is thinking about the RG flow in terms of how fast operators spread. I don't know how to do that, but I think it would be interesting to try to study RG flows in that language.
So Tom, if the spread of T mu is trivial, does it mean that there's no RG flow? Does it mean that the space is ADS?
No, there can still be RG flow. It just means that along that RG flow, the Goldstone theory is Gaussian. OK, so that's the story in ADS. And now we're going to go back and see what, if anything, we can learn about de Sitter, which was the original problem that motivated this. So as I said in words, the derivation of the dispersion relation involves a contour deformation from the IR to the UV. So schematically, the way this dispersion relation comes about is you calculate the DIS amplitude in the infrared. You do a contour integral in the infrared. So in this case, I'm drawing this on the x plane. X is this momentum transfer. So small x is the UV. Sorry, 1 over x was the momentum. So small x is the UV, large x is the IR. So you start with a contour integral in the IR that picks off the piece of the amplitude that you want. In this case, it was our speed of infall. And then you take this contour in the infrared and you deform it around the cut in the UV, and that's what gives you the cross section because you get the discontinuity across this cut. So that's where the dispersion relations came from. In the IR part of this, everything carries over easily from anti-de Sitter to de Sitter. Okay, so everything I said about calculating Witten diagrams and the effective theory and writing the 4-point functions, everything there you can just Wick rotate easily to de Sitter. It's just a kinematic change of variables. The fact that there's some infrared piece of the amplitude that's related to these coupling constants in ADS, you can immediately Wick rotate to DS, and you get some corresponding relationship between a de Sitter DIS amplitude and the speed of sound and inflation. So the radial infall speed changes to 1 over the speed of sound. So the dispersion relation just translates this way. The thing showing up on the right-hand side here is a strange object. This is not an inflationary correlation function because when you Wick rotate from ADS to DS, you don't get correlation functions. You get variations of the wave function. But this is something that we understand how to calculate in de Sitter, and maybe is not. If you were just a purely de Sitter person, this would feel like a strange thing to stick in a dispersion relation, some moments of the wave function. But this is what this procedure is telling us to do. We can take these pieces of the wave function and plug them in to read off the coupling constants. We don't know of a way to do it in terms of the correlators, the de Sitter correlators. Yeah. I mean, it's the same information in there, so you would think that it could be translated, but.
And the correlators might involve this also, this piece of the wave function.
Yeah, that could be, but we don't know how to do it. So that part of the argument still works in de Sitter. However, we don't know the UV behavior of this wave function in de Sitter. It's not a duality anymore to a conformal field theory at Scri+, at least not an ordinary one. So in inflation, the best we can do without making any further assumptions is say that, well, we can deform this contour, but it just becomes some mess in the UV that we don't really understand. Okay, so it's still true. It's still true that the things that you measure, like the inflationary speed of sound, tell you something about the UV, but we don't really understand the analytic properties in order to be able to say, for example, that it's positive. Yes?
When you say UV, you mean from the point of view of the CFT or from the point of view of the CFT?
I mean from the point of view of the, so yeah, what do I mean by UV? I mean we take the de Sitter wave function, act like it's a correlation function, continue in momentum to some strange complex momentum that corresponds to this DIS amplitude, and then take that DIS x to 0. So this is not a very physical.
So it could be late time as well.
I think it corresponds to a late time limit, right? And we know, yeah.
Sir, is it obvious that there is no branch cuts coming from infinity?
Let's see. Yeah, we know enough about, yeah. Yeah, we know exactly where these branch cuts end. I don't remember the formula, but just from the properties of the CFT 4-point function, we know where they end, and so they don't go past those points.
Is it applicable also for DS?
Sorry?
Is it applicable also for this DS case?
You mean this fact about the branch cuts?
Yeah.
Yes, the correlation function that we're calculating is calculated by the same set of Witten diagrams in DS as it was in ADS. So as long as you're just talking about the perturbative calculation of the Witten diagrams, we know where all the cuts are and everything. It's only when you start trying to go into the UV that you don't know the properties of the correlation function. Okay, so in DS, that's sort of as far as we can go. It's true that a measurement of the CMB that tells us that the speed of sound is very close to 1 would tell us something about the UV amplitude, and it's something interesting. If we found the left-hand side is 0, well, then the right-hand side has to either vanish or there has to be some crazy cancellation, but that's as much as we can say. We don't know in particular that the right-hand side is the integral of something positive, and therefore we can't necessarily conclude the theory is free as CS goes to 1, which was one of the goals, but doesn't seem to be possible with this method. So on the other hand, this integrand is positive if you just take a QFT in de Sitter and you just study this amplitude in that QFT, then in the examples that we know of, this thing on the right-hand side is positive. So if you go out and you measure things and you learn that it has to be negative, well, that would tell you that that's where the quantum field theory has to be breaking down in order to get the negative contribution. But really understanding the UV properties of this de Sitter amplitude is a difficult problem. It's related to the late time behavior. And so I think a natural guess is that if inflation lasts a very long time, then it should be as if there really is good behavior in the UV and that the number of E-folds of inflation is related to how strange this UV correlator could be. But I don't really know how to make that into a precise equality. Okay, so I'm going to conclude there. So in ADS, we derived a dispersion relation for how fast trace T spreads. I think a clear question about this, and this was actually part of what motivated looking at this quantity, is the connection to C theorems. So C theorems are also sign constraints along an RG. C theorems are also, well, like the Komargadsky and Schwimmer derivation of the A theorem relies on a very similar type of term. They're looking at dispersive constraints on the trace T 4-point function. It's a slightly different constraint, than a slightly different amplitude than the one that we studied, and it doesn't seem to be the same constraint. But it'd be interesting to understand how these are related to each other. So then in inflation, we found a similar dispersion relation connecting the IR to the UV, but without the strong constraint that you get from unitarity. And I would say that the rules of QFT during inflation are murky, but something that I think we can still make progress on understanding better. Okay, thank you.